And then A is what we call the growth or decay factor. And that number is the number that we're repeatedly multiplying by. So every time we increase x by 1, we're multiplying by another factor of A. So remember, we talked yesterday about how that's related to the growth or decay rate as a percentage. So A is equal to 1 plus R, where R is the constant percent rate of change. So this relationship right here, just from experience in past semesters, will answer like 90% of the questions that you have when you're like, oh, I'm not sure what to do here, or how to get what it is I'm looking for. It's because the tricky part of these is just going back and forth between like the percent rate and then that decay or growth factor, because the decay or growth factor is what's in your function, but the percent rate of change is what they typically give you as far as like explaining how the y values are changing over time. So we need that A equals 1 plus R to relate those two things so that we can go back and forth between what we're given and what we need for our function. So with those in mind, go ahead and write two functions here for the number of students T years after 2010. And then we'll do a few more problems that are a little bit more detailed. What we're given here is called, I don't really like putting it right there, I'll put it right here. It's called absolute change. Which means that what we're given is a change that isn't dependent on what the value was previously. So how much how many students are added each year doesn't depend on how many students there were the previous year, right? So it's always just 500. So it's an absolute number of people. And that's the characteristic that we look for when we're looking at linear functions. So linear functions, how many students we're adding or how much the y value is changing each time we increase x doesn't have anything to do with what the y value was for the previous x value. Whereas when we look at an increase of 20%, we don't know how many students to add unless we know what we're taking 20% of, right? So unless we know how many students there were the previous year. And so the change in the number of students is relative to how many students there were before. So we call this a relative change. And that's really what you want to look for when you ask yourself, is this going to be a linear relationship or is this going to be an exponential relationship? Is a good question to ask is, in order to figure out how many more students or money or whatever there are, do I need to know how many there were last year or last whatever it happens to be? If you do, then it's likely a relative change and therefore an exponential relationship. If it's a set number that they give you to add on, so you don't need to know anything about the previous year or month or day or hour in order to know how many to add, then it's an absolute change, and that's always a linear relationship. So this first one is a linear relationship, which means f of t is equal to our initial value of 1,000 plus 500t. And then In part B, we have relative change, which means this is an exponential relationship. So we have f of t equals 1,000 times our growth factor, which again is 1 plus our growth rate. So they give us this 20%. That tells us that r is equal to a positive 0.2. And it's positive because it's growing, so because that population is increasing. So you always want to ask yourself if that r value is positive or negative, because it won't be, like, they won't use a negative sign on that 20%. They'll just say the word like decreasing. So if it decreases by 20%, then we know it's a negative. And so a is equal to 1 plus r, and that's how we get our 0.2. And then that's to the t power. So let's see. I printed out the rest of these just because they're a little bit wordier. So half-life is used in a lot of different ways, but probably the one that most of us have heard of is carbon dating, right? So it's how they determine how old something is. So like when they find bones or remains like in the desert and they tell us that it's like 20 million years old, the way they figure that out is using what's called carbon dating, which is looking at the chemical makeup of the substance and using half-life of a certain type of carbon to determine how much is left of the original amount, and that's how they figure out how old it is. So when we talk about the half-life of a substance, the half-life is an amount of time. So it's the amount of time it takes for the sample to decay by 50%. And so when we talk about half-life in this setting, so we're talking about periodic growth and decay. We will do instantaneous growth and decay next week, and so it'll be a little bit different than this. But for now, the decay rate is always the same when we talk about half-life, because we're always talking about a period of time that causes it to decay by 50%. So how long it takes for there to be half of the original amount left. And so in this case, when I write these functions, I always think about what x represents, what my initial value is, what my growth or decay rate is, and then what my growth or decay factor is. Sometimes you won't need the growth or decay rate. For instance, if they tell you that like something is tripling every hour, they're telling you that the growth factor is 3, that you're multiplying by 3 every hour. So you never actually need that growth or decay rate because you already have your a to write a function. So here our x is the number of half-lives. And when we say number of half-lives, we just mean the number of 200-year periods. So 400 years would be like 2 half-lives. 200 years would be 1 half-life. C is the original amount we start with, which is 100. And then R is our decay rate, which in this case is going to be negative 50%. It's decay, which is why that rate is negative, and it's 50% because the half-life refers to how long it takes to decay by 50%, so decay by half. And so this is negative 0.5, and then that means A is 1 plus negative 0.5, which is 0.5. And so now we can write our function f of x equals 100 times 0.5 to the x. One thing to notice is that your exponent, that time period always has to correspond to how long it takes to decay by whatever the decay rate is, right? So if we said x was the number of years, that would be saying that every single year our sample decayed by 50%. So whatever time period your variable represents, your exponent represents, is the amount of time it takes for that decay or growth to happen. So if I say that something grows at a rate of 20% per month, then my exponent has to be the number of months, because that corresponds to how long it takes for that change to occur. Because it's not linear, so it's not the type of thing where if you say that it grows by 20% per year, you can just divide that by 12 and then make your variable months, right? So that correspondence is one of the most important things about these exponential relationships. So when we get to the second part of this problem, if I want to know how much is left after 1,250 years, I can't just say x is 1,250, because that would mean that 1,250 half-lives have passed, so 200-year periods have passed, which isn't the case. So we have to figure out what x is first, and to figure that out, we take the number of years and just divide that by the half-life. So the number of years divided by the length of the period that our variable represents. So that's 1,250 divided by 200, which gives us 6.25. And so now we can evaluate our function. So f of 6.25 equals, I say 100 times 0.5 to the 6.25. And what's that give us? Go ahead and put that in your calculator. And what do we get? 1.31 grams. No, just round to what seems reasonable. 1.31 seems pretty reasonable in this case. In the last one, we'll round to the 10th place because we're estimating, and so we're going to have to use some trial and error here because we haven't covered logarithms yet, which is how we would solve for a variable in the exponent. So in this case, we are trying to find where our output is 1. And so we're looking for an amount of time, but we need logarithms to solve for an unknown exponent, which we don't have yet, so we're going to just use some trial and error to estimate. Where should we start, do you think? Like, if I was just going to guess at what my x value should be, what do you think?
We just found out that 1,250 years is 1.31. I would assume it's less.
Would it be less? You don't need your calculator to figure it out. If less time has passed, more time, right? Because we are losing matter. We're losing some of our sample. And so if it took 6.25 half-lives to get to 1.31 grams, it's going to take longer than that to get to 1 gram, right? So what do you think? You want to try 7? So let's do f of 7. What do you get? 0.7. So that's a bit too far, right? And in these problems, you have to remember like how quickly this is decaying, right? If we add one more half-life, what would happen to the amount that we have left? Like if I increase that to 7.25. What would happen to that 1.31? How much would that change by in one half-life? Don't need a calculator for that one either. One more what? So it'd be one more half-life, but what happens to the amount of the sample when one half-life passes? Yeah, there would only be half of it left, right? So if we were to increase our X value to 7.25, only 0.65 grams would remain, right? Because after one more half-life, we've reduced the amount of the sample by another half. And so this is happening fairly quickly. It's going down pretty quick. So even increasing up to 7 is going to be we're almost reducing it by half, right? Because we've almost increased our X value by 1. So we should probably go up relatively little because that 1.31 is pretty close already. So maybe, I don't know, give me another guess. Sure, let's try 6.5. What's that give us? 1.1. So we're pretty close, not quite far enough, but it's just a matter of kind of how you want to think about the numbers relative to what's actually happening, right? It seems like an increase from 6.5 to 7 wouldn't do much because that's a small increase. But because this is decaying so quickly in terms of the number of half-lives, maybe 6.6. So remember, we have to keep going up because the amount is going down. So if we're too high, if the amount of substance is too much, then we need to increase our time. So 6.6 should give us, it rounds to 1.0. It's 1.03, I think, grams. So what is that 6.6? What did I just find out? Yeah, that it takes 6.6 half-lives. So how many years will it take? How would I figure that out? Yeah, 200, but yes, that's the right idea, is to multiply the number of half-lives by the amount of time in one half-life. So number of half-lives times the half-life. So we have 6.6 times 200 equals 320 years. So it would take 1,320 years for that to go down from 100 grams to 1 gram. And so again, the tricky part of this is just thinking about the period of time correctly, right? Remembering what your X represents in terms of the number of half-lives rather than the number of years. So let's look at rabbits. I'm sorry I didn't give you more space on this one, but we won't need that much space. We're just going to write a function. So if X is the number of months, we have our starting amount, our percent rate, and then our growth factor. Our starting amount is 2. And then do they give us the percent growth rate or the growth factor in this case? Yeah, they give the growth factor because they actually tell us what number we're multiplying by, right? If we're doubling, that means that we're multiplying the number of rabbits by 2 every month. So we don't even need this growth rate here because it's not part of the information they give us, and it's also not part of the function we're writing, so it's not necessary. We needed it before because they gave us that, and then we used it to find the growth factor. What's up, Shelby? So if something doubles, that means we multiply it by 2, right? It would go 2, 4, 8. So that's how we got that our growth factor is 2. Right. If they said it increases by 100%, that would be R equals 1, which would give us the same thing. But when they say doubles or triples, that means that they're actually telling us what number to multiply by, which is the big difference between the growth rate and the growth factor. The growth factor is always the number you're actually multiplying by to move through time. And so we have f of x equals 2 times 2 to the x. How many rabbits will there be after 5 years? Go ahead and just do that on the side somewhere, or even just on your calculator.
64.
64 rabbits?
Yeah.
Do you guys agree? So after 5 years. So just out of curiosity, does that seem reasonable? Like what we know about rabbits, that they go from 2 to 64 in 5 years? What's up, Caitlin?
X is the number of months.
Yeah, X is the number of months, right? So if we put 5 in for our X value, that would mean that it doubled every year, not every month. So after 5 years, our X value is 60, right? Because 60 months has passed. Good. So f of 60 is what? Whoops, not 6. What is it? 120? That seems low. I think that's what you get if you multiply 2 by 60. We want to raise 2 to the 60 power. What do we got?
I got a giant number.
Uh-huh.
I got a 2.3 number to change and then E18.
To the 18th. So 2, and then so what that e to the E18 means is times 10 to the 18th. So you said you got 2.3.
Yeah.
So if it says E18, it's saying times 10 to the 18th power. So that would be 2, and then at the decimal point, start counting. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm not even going to try to say that number in words because it's like million, billion, trillion. I don't know. Do you guys know what comes after trillion? Quadrillion, I think it is. And I'm not sure what happens after quadrillion. Quintillion seems reasonable. So 200, million, billion, trillion, quadrillion, quintillion, and then it hexillion, 2.3 hexillion rabbits. That makes more sense though, right? Because rabbits multiply quickly. And when you double something, like at first it doesn't seem like much is happening. Like, I think, is it on your homework? You'll do it with pennies. Like you do, like where you double your money every day. So you start with 1 penny and double your money every day. You would be surprised at how quickly you have a lot of money. Because doubling means, so yes, in the first day you're only adding a penny, right? But the second day you add 2 pennies, and then you add 4 pennies, and you're going to add 100 pennies pretty quickly, right? So I'll let you see what happens tonight on your homework. But when you double things, they get big really fast. You guys have heard the term something growing exponentially, right? Which just means that it kind of blows up. It gets really big really fast because that rate of increase is getting bigger and bigger and bigger and bigger. It's growing faster and faster and faster over time. So last one, geese. I think geese are my least favorite animal in the whole wide world. They're just kind of gross. They're yucky. And I've heard they're really mean as well. I've never encountered a mean goose, but when I was little, like, there were lots of geese at the parks, and they were really yucky. Like there was like goose like droppings everywhere. So yucky. So yucky. I don't like geese. And they bite. I heard they have teeth in their beaks, which is really frightening. The only thing more like scary than like beaks with teeth is like fish with teeth are really scary too. It's just not how it's supposed to be. Okay, what was the goose population in 1980? So 170.8 thousand. Good. And so that means that when we're writing our function, C is going to be 170.8. Be careful with that thousand. If we're counting in thousands, we don't include the 1,000 in our C value, because that's actually the number that you get as your output, as opposed to the actual number of geese there are. And then if I want to determine an exponential model, well, I know what C is. I don't know what A or R is. So I can say S of t equals 170.8 times a to the t, just to put everything down that we know. But we can't calculate our percent rate of change the way we have, like we did yesterday, because the 2 points we have don't differ by 1. Remember we said that our percent rate assumes that we're only increasing our x value by 1. And so like theoretically I could make my t 20-year periods and I could calculate my percent rate of change over 20 years, but that wouldn't be a very exact model, and we already said t has to be the number of years, right? Not the number of 20-year periods. And so unfortunately we can't just take the rate for 20 years and divide it by 20 and get the rate for 1 year. It doesn't work that way, right? Because we can see it gets steeper and steeper and steeper. And so that 20% isn't like divided evenly over that 20 years. So instead, we're going to use the same approach that we used with quadratic functions. We know the form of the function, and we have a point. So if we plug that point in, we can solve for a. So we're going to say our output is 837.4 when our input is 20. And this we do know how to solve because our unknown is not a variable. So we'll need logarithms to solve when our unknown is a variable, but this one we can do. So we're going to divide 837.4 by 170.8. And if you want to write that as a rounded decimal, that's okay. But when you actually do the calculation, don't use a rounded number. So you never want to round in intermediate steps, because the sooner you round in a problem, the more times you have to round and the further and further away you get from the exact answer. Like, that's why our roofs probably fell down on our gyms, is somebody rounded in an intermediate step. Not a good idea. Let's watch things fall down. So you can either leave it like this and then plug it in like that, or I will show you how to use your calculator to save that information. So we want, like, this is like 4.9-ish. And we want to take the 20th root of both sides. And there's a couple ways to do that on your calculator. So, and I knew to round that to 4 decimal places just because it told me in the problem to do that. And so S of t is equal to 170.8 times 1.0827 to the t power. What is the percent rate of growth over 1 year? Yeah, so as a decimal, it's 0.0827. As a percent, it's like 8.27, right? And we got that because we know that A is equal to 1 plus R. Good. I'm telling you, like, I want you guys to dream that equation. It's super important. So that's 1.0827 equals 1 plus R. You can solve for R. If you just know that equation, you can probably figure out what R is just by looking at it. So you definitely don't have to write it down. So that would be an 8.27% growth per year. So now let's estimate the current snow goose population. So in the year 2019, what would, using your function, what would our snow goose population be? So what should my t value be? Yeah, 39. Because in 2019, it's been 39 years since 1980. And as far as where we're starting time-wise, that has to correspond to your C value. So the number of geese in 1980 is 170.8 thousand. So because I use that as my C value, I have to use 1980 as t equals 0. What'd we get? It's pretty big. 3,787. And then that's 1,000, so, well, I shouldn't do it that way. So I get that, and then that is 3,787,000 geese. You think that answer is realistic? I have no idea how we would determine if it's realistic. I didn't write this problem, but somebody in my other class said they didn't think